My name is Pieter. I'm a principal scientist at Sofar Ocean. At Sofar, we work with ship owners to help optimize their vessels and principally to help optimize their guidance. So we try to help them operate their vessels such they maximize economic gains while also taking into account crew safety and vessel safety. Now, one of the new things in the industry is that with increased regulations, with the need to increase fuel savings, we are more and more looking into, can we reintroduce sails or wind-assisted propulsion to help capture additional savings to maximize the economic gains and also reduce carbon emissions. And in this talk, I want to talk a little bit about how at Sofar we incorporate wind-assisted propulsion, and specifically how we incorporate it into the way we model the vessel and how it affects how we optimize for the vessel. Now, to start, I want to talk a little bit about, in general, when you talk about vessel optimization or weather-based optimization, what you need to know about a vessel. And in principle, how do you need to model a vessel? At Sofar, we call this particular part how we model the vessel, a vessel performance model. This is also sometimes referred to as a digital twin of the vessel, but the idea is the same. What we want to know is how a vessel performs, and specifically we want to know if the captain sets the RPM to, say, 65, and we know the weather, and from Sofar we have very good weather forecasts, specifically of waves and of winds and of currents. So if we know the weather and we know the RPM, how fast will the vessel go? How much fuel will it consume? Those are the two basic things you need to know in order to then start making decisions. Okay, if I change the RPM, how will that affect my fuel consumption and my speed? And consequently, how will that affect the total fuel costs and my arrival time? And it's the tension between the costs of time. I want to arrive as fast as I can, because in general, the faster I go, the more economic gains I get, the more trips I can make, versus I also want to minimize my fuel costs, because that is my principal cost over the voyage. Now, to answer this question, how much fuel do I burn and how fast do I go? So far, we use a VPM that is based on a combination of physics-based principles and data-driven optimization. And the basics is as follows. We start with well-known naval architectural rules from the literature, and we describe a vessel by a force balance. We assume that at a given cruising speed, say 12 knots, the forces on the vessel, so the force by the prop that moves it forward, is balanced by the resistance. And this is typically the hull friction, the wave making of the vessel, and this can also be the impact of the environment. Think waves, think wind. If this force balance, if the propeller is balanced by the friction, then the vessel is going at a steady state. Now, and for each of these terms in the force balance, we use the rules from naval architecture. We have the ITTC descriptions for the frictions. We have Holtrop and Menon for the wave making. And in general, for all of these different components, we use well-known and validated rules from naval architecture. And these help us describe, in general, how a vessel behaves under different conditions. However, that is for a general class of vessel. So in that way, we can describe a bulker, a container vessel, a PCC, different types of vessel. But it's not a specific vessel yet. And to make that model specific, we add data-driven component. And specifically what we do, we take data from the vessel, reported noon reports, increasingly in the market, also high frequency data is becoming a thing, but right now it's mostly noon reports. And we use these noon reports to tune the model that we have to fit what the vessel actually did. And in this way, we're able to create very, very precise digital twins of the vessel that help us predict how will this vessel perform under different conditions. And again, that in turn can immediately be input to things like a route optimization engine, which essentially tries millions of different routes with millions of different settings of RPM to find what is the optimal route and speed of the vessel. Now, this is essentially in absence of wind propulsion yet. But the nice thing of our formulation is that it is relatively straightforward to add wind propulsion to this component. All we do is we add an additional propulsive component to our force balance. Essentially, what happens is that in the model, once a wind-assisted ship becomes on platform, we enable an additional propulsive force in the balance that represents the sail propulsion. And in this way, the rest of the platform actually doesn't change on Wayfinder. The optimization engine doesn't change, how the system operates doesn't change. What changes underneath is only the digital twin of the vessel, essentially, or the vessel's performance model, which now can take advantage of wind if suitable. What is important, obviously, is how do you describe that sail propulsion? Because that is non-trivial, and that will be different. There are different types of sails, right? You have suction sails, you have rotor sails, you have more aerofoil-based sails. And so for each of them, the propulsive force will be different. How that typically we handle that in Wayfinder, and we have, because we've worked with different manufacturers of different types of sails, is that we introduce a sail thrust response function. And you see an example of this here on the right, where in general, the darker colors will mean higher values, and you're looking at the additional thrust provided by the sail as a function of the direction, which is on the radial as you go around the circle, and the wind speed, which is if you go along the radius of the circle. So if I were to say, in this particular case, have a beam wind 45 degrees from the vessel, and the wind speed will be 10 knots, I will be in the light green kind of shaded region, and I would get that particular forward thrust given to me by the sails. And so this sail thrust response function essentially summarizes for different conditions, different wind speeds, different relative wave directions, what the additional thrust by the sails is. And so once we have this sort of, you can almost call this a fingerprint of the sail, right? Each of the sail has its own fingerprint, which is unique to the sail, and it comes from the sail manufacturer. And they typically get these fingerprints once you do wind tunnel tests. So you try one of these sails in a wind tunnel. Once you have this fingerprint, we can put it into the optimization engine, and it can make use of it to say, okay, if I would position the vessel here, I might catch this, 10 knot beam wind, which is highly favorable. Whereas if I were 100 meters to the south, the wind would be from the stern and will be less favorable to me. And so in that sense, it allows the optimization engine to incorporate these kind of trade-offs. This is sort of what allows us to estimate the performance in different types of weather. Here, for example, you see the speed fuel curve for the same wind speed, 14 knots, but at different angles of the wind. And so you're looking at the main engine fuel consumption on the vertical. You're looking at the vessel speed on the horizontal. So this is a speed fuel curve. And what you're looking at here is essentially for the lower plot, the fuel consumption as given if the wind comes from the beam versus the fuel consumption if the wind comes from the bow. Most sailing vessels prefer the wind to come from the beam, because that will give you maximum thrust. And in this case, you see that we get a pretty appreciable reduction in fuel consumption once we get a bow wind versus a beam wind. There are also different components, right? Because once you have a bow wind, you will also actually get bow waves, because wind and waves are generally aligned, so that will also increase fuel consumption a little bit. So there are different components to why the fuel consumption is higher under a bow wind, but in general, this is mostly the effect of the waves. Again, given these relationships, we can now use this to drive the optimization and see what is the most favorable heading of the vessel, the most favorable position to optimize fuel consumption and economic gains. And I want to give here a example here. This is a rotor vessel that we outfitted with generic rotor sails. So an example of how a sail might behave. And the vessel is traveling to round the Cape of Africa. And here, what you see is a vessel without optimization and a vessel with optimization. Where with optimization, the vessel is the black line, and is the magenta line. Black line is without optimization. In this particular case, we want to look at, okay, once you add sails, you get a general benefit from the sail. So the sail will help you in general save some fuel, but you also might want to change your decisions now, because now you might want to deviate from the shortest route to catch the wind, as it were, right? You might want to say, hey, I might take a little bit of a longer route, but catch that favorable wind and so come out ahead. You might almost compare it to being on a bike and taking instead of taking the shortest route, which might have a big hill and you want to avoid, you want to take the downhill part, which might be longer. In the end, you'll still be faster. This is kind of similar to that extent. But making that trade-off is pretty hard, because it's, at least like for a human, intuitively, because you have to sort of guess, okay, how much will I save in fuel? And I might also go a little faster because a little extra push from the wind, versus, but I'm also going a longer route. And it is that trade-off that an optimization engine helps you with and helps you decide with, and why I think wind propulsion and route optimization should go hand in hand, because it is very hard for individuals to make that decision on their own. And this is where Wayfinder, I think, really excels in terms of value proposition, because it can help you make these decisions. I think one of the key, misunderstandings of wind propulsion and optimization is that there's often an over-index on fuel saving. And so you see examples where vessels will take large deviations and will save a lot of fuel compared to the direct route. And at first, that sounds great. You saved a lot of fuel, but they neglect the fact that they arrive 5, 6, 7 days later. And that's an opportunity cost. You've just lost 7 days of trading, and that also costs you money. And so you are not free to just deviate at will. You have to make that decision rationally. And you can see that here, where the system in the beginning decides to take a slight deviation, because as it takes a deviation, it catches some favorable winds, which sort of come from the bow. And as a consequence, it saves some fuel and overall economically comes out ahead. In the end, you see it also actually making a slight detour near Africa. That particular detour is actually driven by the Agulhas, which is there, which also gives you a nice little bump. And so you're not just want to ride the wind, you also want to ride the currents. But in general, I think this is a good example of how wind-assisted propulsion will influence your decision-making in routing. You will start making small deviations to catch some favorable winds, while generally keeping to your routes. I think one of the other core advantages that we've had in the way that we implemented things is that because we implemented it into a force balance and we have these physics-based underpinnings, we can actually extract which of the components contribute to the thrust or to the total resistance. And so we can attribute when the sails are most effective versus when they're not so effective. And you can see, for example, a breakdown here on the right where the total resistance, which we shaded here in red, given in kilonewton on the vertical, and there's the date time on the horizontal. The total resistance is shaded in red, and that's balanced by the propeller thrust and the sail thrust. And you can sort of see the breakdown that in general, your propeller will provide the majority of the thrust. And this is for the same example you just saw the animation of. But every now and then, actually the wind provides even the majority of the propulsion. And I think this is, again, a good illustration how in general wind assisted propulsion will function. Given the route you and the weather, you are not always able to find favorable winds. And so over stretches of your voyage, you will not gain a lot of extra thrust from the sails. But during portions of the voyage, you will gain a lot of extra benefits. And that is sort of this intermittent nature of wind assisted propulsion, again, is what makes it harder in operations and why combining it with optimization is really key. And one of the things that we've done here to make this a little bit more insightful as well, and also to help owners estimate how much returns you actually get from your sale, is to re-express this terms of force balance in terms of energy balances, and to tell you a little bit about, well, the force balance, force times velocity is energy or is power. And so you can essentially reformulate a force balance to an energy balance. And that way you can attribute how much energy is generated by the engine for the propulsive, how much energy is generated by the wind, that for your propulsive force. And you can use those estimates and convert that energy back into fuel. Now, for energy by an engine, there's a direct relationship. Energy generated, net energy generated by an engine comes from the combustion of fuel oil. And so there's obviously a direct relationship to the main engine fuel consumption. However, the same energy that's generated by the wind, you can convert using the same conversion principles to an equivalent fuel. In other words, the sails generated this much force, which is equivalent to so much power, which over a day or over a time period is equivalent to a certain amount of energy. And we can convert that energy back to fuel. And that gives you a direct measure in, hey, it's not only this percentage of the propulsion that the sales gave, but it gives you insight in, okay, and that means that we saved 2, 3, 4 metric tons a day of fuel because we added sails to this vessel. And I think those kind of insights are crucial, because ultimately installing a sail on a vessel is not free. And anybody who installs the vessel or the sails will want to know what your return of investment is over a certain period of time. And to do that and to see if you're operating the sails as efficiently as you can, you need to estimate, like, how is their contribution compared to my actual cost, the fuel cost. And so if you can express it in terms of fuel and consequently in terms of money, because fuel costs money, you can actually say, okay, the sails actually saved me X amount of dollars, and consequently in Y amount of time, we will recuperate or even start profiting from the sails, right? Because ultimately that is the goal. And this is essentially what we've done here on the right, again, for the same voyage that you saw before, express that in terms of fuel savings. And what you see here in blue are the total fuel consumption of the vessel, the percent saved. So that's what we try to do here in this graph. What you see here on the right are the actual fuel savings you get from a sail operated in the example we saw before. In green here, you see the actual fuel savings in metric ton a day. And again, what you see is very intermittent. And this is, again, associated with the fact that sometimes you catch a favorable wind and you might save up to 10, 12 metric tons a day, which is substantial. And in other lulls, you might not actually get a meaningful contribution from the sail at all. And so sometimes when you're at 10, 12 metric tons, you might be up to 40% or more of your total fuel that you're saving, compared to if you did not have the sails. And so this insight can really give you an idea of your overall savings, which will be the average of this graphs, but also, like, look, these are the conditions where we maximize the ship, where it's operating as efficient as possible, whereas these are conditions where the ship won't be as efficient. And those kind of considerations are really important once you start thinking about where should I utilize my asset. Because you can imagine, if I know under what conditions my vessel operates optimally, you want to operate that vessel in along routes where those conditions are most likely. And I think that is really the key, and why these type of insights and why the detail of these type of insights can be very, very interesting and important. Again, I think, and this is coming back to this sort of more forward-looking or planning kind of thing, the way we set up the system also makes it very easy for someone to start considering, well, we have, maybe you have vessels on platform, and you might be considering, well, on this particular route, we would consider for this Cape-size carrier or what have you, to install rotor sails or other types of sails. And we would like to know, what would the benefit of that be approximately? Can we estimate on this route, on average, what the returns will be? And a system like Wayfinder, because of the way we set it up, pretty easily allows you to do that. We can add a rotor to the vessel that's on platform and say, okay, what if we enable propulsion and imagine that the ship had the wind propulsion? Like, how would that affect the ship? How much fuel would you save? We could simulate 1 to 10 vessel voyages and say, okay, well, that means over these last 10 voyages, you did X. With the sails, you probably would have saved 5, 6, 7% on your fuel. And depending on your strategy, you might be a little faster, a little slower. That depends a little on economics. But in the end of the day, you can estimate how much you come ahead. And that in turn can help you decide, look, is it worth it for this particular route? And what would the return of investment be on this kind of investment? To give a little bit of an idea, in general, like, what does wind assisted propulsion do, and how much does it affect this? There's sort of two components you look at. On one hand, you want to look at, okay, how much in general does optimization add to my vessel? Like, I'm operating the vessel right now as I am, and how much more efficiency gains can I get from, say, a platform like Wayfinder? And then you can ask, how much extra benefit will I get from installing the sails on average? What have you seen? Now, adding sails to vessels in general, the benefits of it will depend on the vessel class, it will depend on the route. So there are some, these are rough estimates, but in general, from operating vessels on platform, we've seen that adding sails to a vessel in general will add about 5 to 6% in terms of efficiency, in terms of reduction in overall costs for a voyage. And this number, 5 to 6%, is proven to be relatively robust. And this comes on top of the fact that with Wayfinder, the platform itself gives you about a 6% gain often, compared to operating, say, in a custom power regime with great circle routes or what have you, or the more traditional routing. And so the combination of the two, and I think there again, where I want to emphasize is that the combination of the two, combining route optimization and combining it with sales, is really where the biggest benefits lie. Because once you start optimizing with sales, you maximize their utilization while still taking into account all the economic constraints that you have. And in those cases, we've seen that on average, you can get 12% of returns. And so that is a substantial saving for owners. And that's what I think makes the platform so attractive to operate for these particular vessels. This concludes what I wanted to chat about today. I think the highest level takeaways that I would love to hope to have conveyed here is that wind assisted propulsion is a new technology that is definitely going to take off, and we'll see more and more utilization. Optimally using wind assisted propulsion requires not only the installation of the sails, but also optimally using them and making good decisions with the sails enabled. And to do that, I think you need both a good way to describe how vessels behave with winds, and this is where we have the vessel performance models in Wayfinder, and where we use our data-driven and physics-based approach to add the sail propulsion to our system. And you need a way to help you make the decisions: should I deviate from my route to catch the favorable wind, or will that add too much distance to my route to make it profitable? And that decision is one that a good optimization platform like Wayfinder can really help you with the decision making to ensure that you operate the sails as economically and efficiently as you can to maximize your returns. So with that, if there are any questions, please feel free to ask.
Audio Jungle.